Welcome. In this segment, we're going to be looking at a one-way ANOVA with a blocking variable. Now, I'm not going to be reviewing the basic components of ANOVA in this video. If a one-way ANOVA is new material to you, please review the other video that talks strictly about a one-way ANOVA. In that video, I take apart all the different components and the outputs so that you can understand it. In this video, we're simply going to build on that idea. We're going to do a one-way ANOVA but include a blocking variable. Now, blocking is one of the most common experimental designs. It's a way for us to increase precision of our results and to control and reduce variation. What blocking does is we take our experimental units and we try and create more homogeneous groups. The treatment is the important factor here. The blocking is simply a way to control, to partition off the extra variation that has nothing to do with the treatment. We simply want to partition off the variation so that when we go to examine the treatment effect, it's not obscuring our results. So in this case, understanding how blocking can be used is important. There's a lot of different criteria. Blocking can be used to deal with proximity, physical sites, time. There's a lot of different ways to control blocking, and you have to understand in your specific experimental design what's the appropriate way to block. We're just going to assume our blocking is set up. And what I mean by blocking, and I'll give you a good example, is say you're dealing with yield, corn yield, and you have a large field. But your field has a gradient. It could be an elevation gradient, it could be a moisture gradient, but all of the different plots in which you're applying your different treatment, levels of fertilizer, for example, we know that this different gradient, where these different plants are, could be affected where they stand on this gradient. But what we're interested in is only the treatment effect. So we create blocks, groups of more homogeneous experimental units. So for example, in the example we're going to look at today, we would create blocks where, in this case, the elevation or the moisture gradient might be more common in this area. So the units, the experimental units within each block are more similar, more homogeneous, and between the blocks, less homogeneous. So blocking is very common. It's very useful, and it's a great way to get a better look at the treatment effect. In this video today, we're going to be looking at one problem in two ways. The first way is without blocking. I'm simply going to run a one-way ANOVA, and I'm going to ignore the blocking effect. We're going to look at the output and see what our ANOVA table tells us. Again, I'm going to be using Tukey's for my pairwise comparison. So let's start off and look at our problem. So what you see in this screen is the data for nitrogen levels. There are 6 different treatments. A researcher wants to study the nitrogen levels across these treatments. The field in which his experiment takes place varies in elevation, so he created 4 homogeneous blocks. Now, in this example, in this first run of our one-way ANOVA, we're going to ignore the blocking. We're simply going to look for a difference across the 6 treatments. In this slide, I've shown you how I set up the data. Again, I'm going to be using Minitab software to run the analysis. So in the Minitab worksheet, you're going to want 3 columns. This is just the first 7 pieces of information. Each observation, our nitrogen level, has 2 pieces of information paired with it, treatment and block. Again, for this first analysis, we're going to ignore the blocking, and then we're going to just run to see about treatments. Our null hypothesis is that there is no difference between these 6 treatment mean levels of nitrogen. Our alternative is that at least one of these treatment means is significantly different from the other. So let's run our first ANOVA, ignoring the blocking. Let's look at the output. What you see here are the steps in Minitab to get you through the analysis. Stat, ANOVA, and then to general linear model. In the response box, you want to enter nitrogen. This is what you measured, what the researcher measured, his response variable. In the model box, we're simply looking at the treatment. You want to click Options and select Adjusted Type 3 Sums of Squares. The Adjusted Type 3 Sums of Squares are a better choice than the Type 1 Sums of Squares, as they can deal with unbalanced design when you perhaps have unequal sample sizes across your treatments. You then want to click Comparison and select Tukey's for your pairwise comparisons. In the Terms box, make sure you enter treatment. Click Results and then select the third button. Now here's our ANOVA table. Remember, we're looking at our treatment effect. We've ignored blocking. We come across here and we look at our p-value. There's a p-value of 0.08. Remember the decision rule. If the p-value is less than alpha, we reject the null hypothesis. In this case, our level of significance is 5%. This p-value is greater than alpha. It tells us that there is no significant difference between the treatment means. In this output from Minitab, we see that all of our 6 treatment groups have the exact same letter. There is no statistically significant difference between the treatment means, even though we're seeing big differences in our treatment means. What's going on here is that there's variation that's obscuring the treatment effect. So how do we deal with this problem? How do we isolate the treatment effect? We know that our mean square error is, inside the mean square error is where all of the variation is going. The blocking variation, that variation due to the heterogeneous nature of the field site, is being put into our MSE. And remember what the MSE is. It's the denominator of our test statistic. So the more variation we have, the harder it's going to see the differences in treatments. So now, let's run this again as we should. An appropriate ANOVA where we include the blocking, where we can partition out that variation due to the blocking so that we can isolate the treatment effect better. So we're going to run this again through Minitab, a one-way ANOVA, but this time in the model statement we're going to include block. So let's look at the output, or the steps through Minitab. As you see this, it's exactly the same way, except right here in the model box, we are going to include block. And it's always good to include a blocking variable first in your model statement. We're not interested in block per se. We're interested in the treatment effect. But we put block first so that we can take care of that variation, partition it away, and then simply look at the treatment effect. All the other steps in Minitab are exactly the same. As you look at the output, our ANOVA table, you see that there's an additional component, our blocking component. You come across and you see a p-value. It's very small. This is telling us that it's important to block here, that it's a significant component in our model. We now look at the p-value for our treatment effect. Remember with the last ANOVA where we didn't include blocking, our p-value was 0.080. Now our p-value is much smaller. We're seeing a significant effect in treatment. It's telling us to reject our null hypothesis. At least one of the treatment means is different across the 6. Also notice here the MSE. In the first ANOVA, the MSE was 16.95. It was much larger. Here, the mean square error is 7.210. A lot of the variation that came from our blocking has been partitioned away from the MSE. It's been put in that blocking component in our ANOVA table. So now when we compute our F statistic, the sums of the squares of the treatment, the MSTR divided by the MSE, that MSE doesn't have all that extra variation into it. It's been separated in our ANOVA table under the blocking component. So now let's look at the rest of the output from Minitab. Here's the grouping information from Tukey's method. Remember, means that do not share a letter are significantly different. So in this case, we see that we have differences. And the biggest difference is that treatment 3 has the highest mean nitrogen level, and it's significantly different from treatments 1 and 5. There's no overlap. They do not share a letter. These treatments are significantly different. Now you look at the rest of this. We see that treatments 2, 3, 4, and 6 are not statistically different from each other. And treatments 1, 2, 4, 5, and 6 are not significantly different from each other. So the big message here is that treatment 3 is greater, significantly greater, or significantly higher levels of nitrogen than treatments 1 and 5. I hope this example of a one-way ANOVA with blocking helps your future analysis. Thanks for joining me today, and see you next time.